focus today is how we use the output of the system in a real application. But this gives you some flavor as to why we couldn't use off-the-shelf components. We needed to design a machine from the ground up in order to have these new components to enable new material properties. And new material properties really is the answer. This is Fortify's digital tooling. And the key material properties here, the strength, stiffness, and heat deflection temperature are the key attributes that help us in this application, are 2 to 3 times higher than prior generations of materials. So we will never claim that we were the first company to have the idea of using 3D printed tools as inserts for the injection molding process. We will certainly claim that we've taken the capabilities some significant steps forward. And the core of that is the material properties, and another piece of it is the training that we do and the tech transfer to help people be successful. But those are the material properties. And this is just a very quick example of a head-to-head comparison, the exact same part with our printed tool. That's a specific test on extruded features. Our tool after 100 shots, and a competitive tool after, well, I guess 0 shots would be the right number. This is like the most difficult thing for 3D printed tools are those extrusions to have them hold their shape. So material properties do translate into benefits in the tools. So we'll spend a few minutes on why consider 3D printed tooling. The 2 most obvious reasons are quick turnaround and lower cost, right? Many times people don't bother with the prototyping step, right? Because when you have to wait 3 to 6 weeks and spend $3,000 to $6,000 to get a mold so you can test the design, that's a long time to wait and a lot of money to spend. So many times the prototype step is not included. And people make an investment in tooling, they get the tools in 6 weeks, and either the design has changed already in 6 weeks, or there's a problem and you have to wait another 6 weeks to get first shots. So the 2 most compelling reasons are being able to bring the cost way down to the point where it's almost not even a concern of a few $100s in a few days to be able to injection mold parts. That takes a lot of the worry out. Those are only 2 of the reasons. In fact, we've identified in our conversations with customers a total of 10 key reasons why customers are interested. Maybe these are the reasons why they brought you to the call today. But again, instead of spending a lot of time going through each of these reasons, these are all available on our website, 3dfortify.com. If you go to the mold tooling tab or the resources tab, you'll easily be able to find your way to lots of sort of reading material and content and ideas about how either captive molders or custom molders are leveraging 3D printed tools to enhance their business. But I think the real goal of people today is to understand, well, okay, let's get to the meat of this here and see how we're actually using this in some real live use cases. So we'll jump into that now. All right, again, back to the website. I know it's probably the 3rd time I've mentioned the resources on our website, but another resource available to you will be a deep dive, a whole book on the best practices for using our injection mold tools. We're going to hit some highlights on our presentation today, but there's always more to the story, and this free download from our website will help anyone that wants to get into a deeper dive at your own pace. That is available. So the first biggest questions we get are, what's the size parts you can run, and how many parts can I get off of a mold tool? So I'll address those and then hand the floor over to Ben McDonald for some more detailed explanations. So the best fit parts are parts that are going to fit in your hand. We love customers that are making like handheld instruments, for instance, but parts that are 5 inches in their longest axis and smaller really fit the use case best. They're smaller, the molds are smaller and less expensive. It leads to lower shot size and pressure, which are important. as well as the full thermal load that the tools need to take, as there's less of a shot to deal with. Complexity, on the other hand, doesn't matter. So we're not at all concerned with textures, images, and things of that nature. That's the beauty of 3D printing, is those features can come for free, where they might be extra burdens on EDM with a traditional steel or aluminum mold. In 3D printing, there's no extra time or cost to achieve textures. And then the next point would be tool life. And really, these are rules of thumb that we'll use here. But the length of tool life, or the number of shots you're going to be able to get off of a 3D printed tool, is really most tied to materials that are being used. With the right materials and adherence to the guidelines, you easily get hundreds of shots in materials like TPU, PVC, acetal, and polypropylene. As we move up into nylons and polycarbonates, we're in the realm of 50 to 100 shots or more. And then as we move into glass-filled nylons, PBT, high temperature, really tough materials, in the dozens of shots, 20 to 50 type shots. These are reasonable rules of thumb that we use. And across the board, the tolerances of about plus or minus 5 thousandths for molded parts is a reasonable expectation from what we've seen across the board. I'm going to hand it off now to Ben McDonald to go into some more detail on some design specifics.
Thanks, Ben. So as you've seen previously in this slide deck, our tools don't look the same as steel. They're orange instead of your traditional silver. And with that being said, we like to treat our tools as different than steel. So that brings a whole set of different design considerations into play to make sure that we're going to be successful when we're actually molding with our tools. So one of the biggest things we need to do is, when we're designing molds for our tools, we need to be a little less aggressive with the features that we're going to include in our tools in order to prolong and maximize the potential life of these tools. So some things like increasing draft angle slightly, it's going to make a big difference on how well your tool is actually able to stand up to the process. So continuing on that thread, venting. We want to make sure that we're maximizing venting wherever possible. This allows us to keep the pressures that we're actually running our molds with down, so that we can properly fill out the part without using unnecessarily high pressures that could potentially put our tools at risk. Some of the best ways we use venting are through inserts, ejector pins. Inserts and ejector pins are really great opportunities for venting, and they also allow for, well, in the case of inserts, they allow for greater design freedom, so you can get a little more creative with what geometries you want to mold. And then ejector pins, they allow you to have a very consistent ejection phase and really keep your process throughout the whole, from start to finish, a standard process, which is super important when we're molding with our tools, as we don't really want to introduce any variation to the process. So this would be a sample picture of the mud frame that we use. What we recommend essentially is all of our tools to be mounted into some sort of frame. In this case, we have our frame pictured here, where we have multiple pocket configurations, which allow us to design our molds for whatever the part geometry is. So we're not using an unnecessary amount of material. At the same time, we're also maintaining general wall thicknesses and whatnot, so that our mold's going to be able to withstand the actual injection process. So for actually ramp up and operating our tools, again, we are different than steel tools, so we're going to have a little bit different of a process in order to properly mold parts. So some of those things are lower pressures, lower injection speeds, and this essentially creates a longer bring up process than you're going to get with a steel tool, but you're going to be much more successful at molding parts with our tools doing this. The real goal is to creep up on that complete fill of a part instead of trying to fill out the part and potentially risk damaging the mold. So as long as you follow these guidelines, you're really not going to put your molds at risk, but they are here for a reason. And like Ben mentioned before, we have this great applications guide on injection molding where you can get a much deeper dive into all of these different design and molding considerations. And it'll really set you up to be successful using this technology in the future. Okay, so let's get into our detailed case study here. A few weeks back, so we were contacted by a group, the ventilatorproject.org, and a little background on them. Their goal was to take or source refurbished ventilators, such as CPAP and BiPAP machines, and they were going to convert them to ventilators to be able to keep up with the demand for the COVID-19 patients. So the problem that they came to us with was that clinicians at hospitals required an alarm module to be in line with the tubing so that they could detect if there was actually airflow going through the tubing. The ventilator project had designed a T-fitting to house this module, and they wanted to prototype this T-fitting in order to test out the geometry as well as get some FDA approval for using that material in a production setting. So sourcing a traditional tool for this part was going to take them like 6 to 8 weeks lead time to get parts, and we were able to do so in 7 days for a lot less than what that final tool would end up costing. So we were successfully able to help them shorten their prototyping phase here with the goal of getting that FDA approval. And we'll dive into kind of how we did it. So first of all, we received the base part design, and we had to design a mold for that part. What we ended up doing was actually taking the part and designing a series of inserts around that part. We did this because for design for these molds, it's a lot easier to remove the inserts and the part from the overall core and cavity block at once, rather than trying to remove inserts one at a time from the core and cavity block. While we were going through this design, we made sure that we were adhering to our own best practices for mold design. So some of that stuff includes draft angles on the part, and we identified that this part maintained a 3 degrees of draft on all necessary faces, so it was a great fit for our process. Besides that, when we went through and designed the inserts actually act as shutoffs in certain areas, and we needed to make sure that we maintained a proper shutoff angle so that our parts would fit together well. This shutoff angle in this case ended up being 15 degrees because we didn't really have too many restrictions on what that angle could be. Typically we want to have a minimum of 5 degrees, but in this case, since we had that extra rim, we were able to go up to 15 degrees. From there, so we reviewed the fit. Yeah, we reviewed the fit of all the inserts in the mold and made sure everything fit properly. And then we just confirmed the placement of our ancillary features, such as our alignment pins, runners, mounting holes, stuff like that. Just making sure that when we release the parts for printing, everything is going to match up what we need it to be. So we ended up releasing those designs for printing, and so another problem that they tasked us with was they didn't exactly know what geometry they wanted to move forward with for the FDA approval process. So they sent us 2 slightly different geometries that they wanted us to design a mold for. So instead of doing 2 separate molds, we ended up creating 2 separate inserts in order to mold these 2 separate geometries. So you can see these inserts are pictured in the green and blue on the right-hand side. Basically, our thought process for this was that Instead of designing the whole core feature as one insert, it would save a little bit of material by designing only half of that core feature as the unique insert. And from there, during the ejection phase, since we're only ejecting half of that insert at a time, we're significantly cutting down on any sort of ejection forces that those cores are going to see, which is only going to be beneficial for us in terms of improving the overall lifetime of this mold. And along with that, we used pins for alignment for these features, just because, especially the green feature, without that alignment pin, it would be floating in air and would be very prone to deflection. So these pins essentially just gave us a little more stability during our molding process so that we wouldn't unnecessarily deflect these core features. And then the other unique part of this design was this two-piece insert here. So this thread section was a particularly interesting section for us to design around, because typically with metal tools, your core or your thread sections are going to be off-the-shelf products or off-the-shelf components. These threads are a non-standard thread type, so there is no off-the-shelf component for these threads. And then to make matters even more difficult, the feature above the thread section has a specific geometry that constrains its rotation. So in order to properly eject all these components, these two parts can't be connected as one insert. They have to be designed as two separate inserts. So what we ended up doing was designing the thread section as a small insert that fits around a extrusion coming out of that second core. This allowed us to properly rotate the insert out of the part before ejecting the second piece. And just to tie this back to steel tools, if you're going to be designing this for a steel tool, this is going to be a completely custom insert piece that's going to take multiple weeks lead time just to source, which that doesn't really jive well with the prototyping process. So this is really a great value add for our technology. So for the actual molding, the part configuration was selected while we were printing the molds. So we didn't end up having to mold both configurations. This part was made out of polypro, so relatively easy material, but the geometries were really what created some difficulty. One thing we'll do before actually molding anything is we'll calculate the part volume, and that includes the runner and the sprue section of the part. And this allows us to properly set our metering position so that we're not going to accidentally overpack our part and run any risks with our molds. So we calculated that volume out to be 22 cubic centimeters. So that led us to setting our metering position, and then our VP changeover position is based on what an 85% fill would be for this part. So we set those parameters, set some other startup parameters such as our material temperature at 500 C. We want to run that at a little bit more at the higher end of your melt temperatures for polypro. And that's just because it allows us to drop the viscosity of the material and effectively use less pressure to mold parts, which leads us to our injection pressure that we set at 2000 PSI. And typically we'll have to iterate on this pressure a little bit. With this particular mold, that 2000 PSI was more than enough to fully fill out the part. And what we'll do there is, instead of adding pressure, we'll add time to that injection phase just to allow more and more material to pack out the cavity. So once we actually got to our 85% fill, that's when we added our pack and hold pressure. So that was 1000 PSI, and that allowed us to fully pack out this part. And this brought us to a total cycle time of just under 160 seconds, which, while that might jump out as long, for the quantities we're looking to do with this technology, it's really a pretty reasonable amount of time. This will lead us into the ejection a little bit here, where we have a multi-stage ejection process So it's going to take a little bit of time. And during that time, we actually have 2 sets of inserts. So we'll have one set of inserts that's actually molded into the part. The other set of inserts we'll put into the machine, and we'll start up our next cycle so that we can maintain some efficiency. With these inserts, so we ejected 3 of those inserts by hand. And those are all very straightforward, and that include that thread section where we're able to just unscrew that by hand with minimal issues. From there, one of the inserts we were able to eject with just a simple arbor press, pressing down on the top face of the core. And the final insert, we had to design a custom ejection jig for, just because it was kind of covered up by the part. So there's no real good way to eject that core without creating something custom. So typically for these inserts, these are the 3 main methods you're going to see when you actually need to eject inserts. Most of the time, probably 70% of the time, it's going to be ejectable by hand. 25% of the time, you'll be able to use an arbor press. And then that last 5%, that's where you might need to get a little creative with some ejection jigs or whatnot. But luckily, we're able to print those jigs with our machine. So I think.
All right. Yeah. Thanks, Ben. I'm just going to run through a couple other success stories. We like that one that we just walked through because it's very relevant and time sensitive. Obviously, it's something that we've done over the past few weeks to participate in the PPE response. And it's one of the more complex ones with the multiple hand loads or the multiple inserts to get it done. But I want to run through some other success stories that we've had working with customers over the past months, and then open to Q&A. This is an automotive application. In this case, the customer just needed 25 parts of glass-filled nylon. That was their goal. They were currently spending $8,000 and waiting 8 weeks to get parts like this fabricated out of aluminum so they could do prototype testing. Our tool, $500, 5 days, and got 50 parts of nylon 6 and 50 parts of the glass-filled nylon. So 100, we got 4 times the shot life out of the tool than was expected. Another case here, these are some standoffs, pipe standoffs that needed to be molded for a company out in the Midwest. In this case, they really were looking at a very fast turnaround. It was a pretty straightforward tool. So the metal tool, the aluminum tool, in this case, was not that expensive, but the time was the big killer for them to be able to get that tool. So in our case, we were able to get them a tool in 3 days. The difference that you'll see in tool cost here is this $500, that's the cost if you own the machine to print the tool. This $1,300 is if you buy the tool from Fortify. So that's why the numbers seem a little inconsistent. In some cases, we sell tools. In other cases, our customers are using the machine, and the cost is based on the actual cost to print a tool. The customer's target of 100 shots was quickly exceeded. And again, another success. This was a torture test we did internally. This was just to prove to ourselves that we could get 1,000 shots off a 3D printed tool. And that was a success. We ended the test after 1,000 shots. And so now we have that as a benchmark. This was a really interesting case we did on it with a company, another Midwest company. And the question here was about repeatability. We ended up having a success on tool life as well. But again, 300 shots was far exceeded the necessary number of shots. But the question this customer had was, are the parts repeatable? The problem they had with using other 3D printed tools was A, the tools didn't last very long, and B, if they did get 20 or 30 shots off the tools, they were all a little different. So we ran our tools, and this, again, the stiffness and the heat deflection temperature of our tools allow us to have a very repeatable process. Here, they even ran our tool on 2 separate days last summer and compared the output on 2 critical dimensions. They actually did 13 dimensions. Here, this is 1 critical dimension. and found that not only were we in tolerance with all of our shots, but we were basically had the same kind of repeatability that they had from their current inventory, which had been run in shots of thousands and thousands of parts on the steel tool. The final case study is a metal injection molding, MIM, or metal injection molding. So this is a really harsh environment. In this case, MIM, if people aren't aware of MIM, MIM is a feedstock of abrasive metal polymer slurry. And the parts are molded in this very abrasive slurry and then sintered in a furnace after. You can see the picture in the lower left-hand corner. That's the molded part. It looks kind of gray, and then you can see that same part after going through a furnace shrinks down, and now you have that's a 17-4 stainless steel solid steel component. And in this case, again, the traditional practice in that industry would be to purchase a metal tool, even at the prototyping stage, a 4 to 6 week lead time. And of course, that tool could be used for thousands of parts, but what's the point of making thousands of parts if you're not even sure it's the right part? So here, for low cost and a quick turnaround time, we're able to get dozens of the parts needed for prototype validation. This customer had tried to use other 3D printed tooling in the past, and for a variety of reasons, mostly having to do with pressure and the abrasiveness of the slurry, did not have success. Our tools held up to the process demands in a very successful way. So what these lessons teach us, and again, I think probably what Ben's the case study around the PPAP machine was that this is a tool you have to learn how to use. If that was the first project Ben McDonald had seen, I doubt we would have turned it around so successfully and so quickly. But because we take the time, we know the process that we developed, we're able to turn projects around very quickly. And the point, I think, of this call is that that's what we've learned about transferring this information to customers, is that making this rapid molding a component of your business, something that you do regularly, you commit how to use this tool, just like you've spent time learning how to use the traditional steel tools. It's not a great fit for once a year or a fire drill. Like, hey, now's the time to learn how to use these tools because we have to get something done in 3 days. The point is to learn how to use the tools now and then be able to constantly or consistently have a fast response time in the future. And then you can really differentiate your shop, whether it's an in-house shop, captive, and be able to provide more design iterations to your in-house engineering teams, or whether you're a custom shop and making these capabilities available to your third-party customers. It's really a way to differentiate your shop and have a consistent ability to turn prototypes around quickly. Next steps that are available, if this is piqued anyone's interest, Fortify has a thing we call our onboarding program. In order to it all stays with that theme of learning how to use the tools. We work side by side with you on 2 projects to transfer our knowledge. And it's a very low risk, low cost way for you to validate that not only can we make this happen in our shop, but that our tools will work on your molds, your designs, your parts in your shop. And of course, our goal in doing this is to develop mold customers and machine customers. Ultimately, Fortify's business is to sell 3D printers. And in this application in particular, our first machines are going out into the field this summer with customers that we've been working with over the past months. So that's the presentation. We're excited now to open things up for Q&A and see what kind of questions we've piqued.
Ben, thank you very much for the very interesting presentation. I really found useful to learn more about these and also to see the case studies. So thank you very much. So I guess we'll open it up for questions. So if people have questions, just feel free to unmute yourself and ask question directly. In the meantime, I see also someone is asking questions here in the chat, so I'll start reading here. So question is, how about the thermal conductivity of your 3D printed material? Is it somehow comparable to steel? How do you deal with high cooling times?
Sure, I'll take an answer on that. So the answer is that this is definitely one of the key differences. Ben mentioned it briefly. We go into it in detail in the applications guide. The thermal conductivity of our tools today is pretty close to polymer, so it's much lower thermal conductivity than either steel or aluminum. And so the way we deal with it is that leads to the longer cycle times. We cool the molds with compressed air on the face of the molds between shots. The heat does transfer, obviously from the face of the mold inward, and we cool it the same way from the face of the mold. Running cooling lines does not really help that much. It's adds a whole burdensome step to the prep time of parts and doesn't add a whole lot of value. So that's the long answer to the short question, but the short answer is that we need to cool the tools with compressed air between shots, and that leads to longer cycle times. But again, the goal of here is less about making each shot have those shortest amount of time, but so instead of saving a minute on cycle time, we're more focused on saving weeks in the time it takes to get the first shots in your hand.
Thank you, Ben. Next question. William is asking, is there any chance of micromolding parts around 1 millimeter?
Without, we'd have to see it's always dangerous to give an answer without seeing parts. We're holding tolerances in the plus or minus 5 thousandths range. As the cavities get smaller, those tolerances actually get a little better. But micro molding, we'd have to take a look at the part to give a qualified answer. The good news about micro molding is there's not a lot of heat transfer, going back to the last question, but typically the tolerances in micro molding would be beyond what we're able to achieve. We'd have to look at the part and the application.
Thanks. Erin is asking, have you done family molds, or do you recommend individual molds for each part?
So I'll tackle this one. We actually have done family molds. Our process, it works no differently if it's an individual mold or a family mold. We just need to be very scientific about how we go and design that family mold. So we want to make sure that we're truly balancing out the runner system so that each part is going to fill out at the same time. Otherwise, we're creating essentially a pressure buildup at the end of fill for one of the cavities. So as long as we're really balancing out those runners well, we can certainly do family molds.
Sounds good. I have another question here. Can you control the shrink rate by air cooling the mold?
Ben,
I'll take this one. I assume we could control the shrink rate by air cooling the mold. It's not really something we've taken a deep look at, but I would imagine just by changing the overall temperature of the air we're blowing at the part, we're going to be changing that shrink rate. So that's certainly something we could do, but we just really haven't taken a look at it.
Sounds very interesting. Thank you. I've got a follow-up from Erin. What is the large shot size you can mold in-house?
Yeah, so the largest shot size we can handle in-house is, I believe it's 23 cubic centimeters, and that varies a little bit by material. So we're assuming a specific gravity of 1 when we're talking about 23 cubic centimeters. If the particular material has a larger specific gravity, then that increases our shot volume a little bit. Or if it has a lower specific gravity than 1, then that will decrease that volume by a little bit. But we're right around 23 cubic centimeters.
Right, and this I just want to make sure that we clarify that that's on our. We have a 30-ton Nisei press at our facility in Boston, and obviously larger machines would have higher capacity. So that's a constraint, not of the 3D printing process. That's a constraint of our molding process.
Sounds good. I have a few more questions. So Daniel is asking, what are the post-processing requirements? Does surface quality change with respect to the molded cycle? And also he's asking about the need for support requirements.
Yeah, I'll tackle this one. For post-processing, so really we have a process of just putting our molds into a sonication bath after printing, and that pretty much cleans our parts for us. From there, we have an oven bake, and then molds are ready to go. For the surface quality, we really haven't seen any degradation of the surface throughout the life cycle of a mold. So I would say no, the surface quality does not change. And then support requirements, most of the time we're able to print our molds without supports. There are a few, and this is like a very few number of instances where we need to support our molds in order to get the geometry to resolve. But we actually don't like to support any of the features inside our molds, as that essentially creates support marks that are left behind on the mold, and it's an area that the molded plastic can grab onto during the actual molding of parts. So we try to stay away from supports as much as possible with our molds.
Thank you for clarifying that. Alex is asking, how do your molds compare to aluminum, known as mud tools?
Sure, I'll take that. So it depends on what's meant by comparison. So in terms of how they're used on the tool, aluminum inserts, they'd be used in a very similar fashion, like the mud frame that we showed would most often be used with aluminum tools. The big difference is, of course, is that our tools are going to not last as long as the aluminum tools, but they'll be in your hands faster at a lower cost. So I mean, that's, if cost and time were not an issue, our value proposition would be a lot less. But since they are, that's really where we fit in on the equation, is an ability to quickly turn around parts and get them in your hands, with some slightly different operating parameters, as we sort of outlined on the call. Hopefully that helps address if there were some specific questions about how they work. I mean, for sure, just going to one of the other first question that was asked about thermal conductivity. Obviously, the thermal conductivity of aluminum is quite higher than steel. So that's definitely a difference between our tools and aluminum as well. So there's different vectors of how we're different. Hopefully that addressed the question.
Thank you, Ben. And people are welcome to follow up with their questions and comments if they like. Gwen is asking, can you guarantee a high gloss surface? So I guess that it ties to what are the surface roughnesses that are typical for your 3D printed tools?
Yeah, I'll take this.
Go ahead.
So our surface finish, it's dependent on the orientation of print. So we can selectively choose surfaces that will have a higher gloss than other surfaces. I think just high gloss surface is a little subjective into each individual's requirement. So I'd love to like dive into that a little more if possible. But what we can do is we can get a pretty, in my opinion, a pretty high gloss surface by keeping an individual surface of the mold parallel to the mold printing direction, or yeah, parallel to the build plate of the mold or of the machine. So this is going to allow us to have one full layer that creates the face of that mold, and that has a pretty good gloss in my opinion. But again, that's a little up to you know, each individual as what they see high gloss.
The thing I would add to that is you always have the option of polishing the tool to a higher surface finish prior to molding. Generally speaking, people don't do that. So I guess that would be, you know, everyone that we're working with here is looking for high quality output of the tools. But in general, the as printed surface finish off the tools is I would say 99% of the time what we run with, because it meets the needs of the application. So again, this is part of our process, right? Is anybody who's like wants to dig in deeper on a specific application, we move this, you know, to a private conversation with exchange drawings, and I think we're pretty good at setting and understanding folks' expectations, and it's just easier to do that around a specific use case.
Thank you, Ben. Thanks, Ben. Next question. Do you guys have any experience with injection molding of rubber when need to keep the mold temperature at 180, 200 degrees C?
Yeah, so
not yet, but we're interested.
Yeah, we haven't been able to find like the right project for that yet. What we have shown is that we can maintain temperatures above 100 C with our molds. So we think that there is a space there for us, but we just haven't found it yet.
Yeah, we haven't ever failed at it.
That's very
but
true.
We'd be very interested to follow up on that and see if there's a fit. The temperatures seem a bit high, but we'd like to explore it with you.
Another question coming in from Anshal. Have you encountered problems with respect to adhesion of the incoming hot melt with the heated insert?
So we actually have in the past. We have a specific coating that we use in our tools that eliminates those problems. And for the trickiest materials in terms of adhesion, pairing that coating with a silicone-based release spray typically solves all problems. So it's not something that is holding us up at all.
Gotcha. Any other
That's
question?
perfect. I think this pretty much sums up our presentation. So I would like to thank Ben Arnold and Ben McDonald, along with Danielle, and obviously Davide for setting up this nice webinar in conjunction with our SB Mold Technology Division. Definitely we'll have more of these type of interesting topic in future. I really admire Fortify to actually pitch into these uncertain times and come up with a solution so rapidly that can be utilized by the frontline people to help us go through this situation. So with that being said, I would really like to thank all of our presenter and obviously Davide and the rest of our ENESB team, as well as the Mole Technology Group, to be part of this presentation and webinar, and we'll definitely keep you posted for any of the future events.
Thanks, everyone.
Great.
You.
Thank you.
Thank you.
Thank you, guys. Yeah.
Thank you. I see Gwen, you raised your hand.
I'm
You-
still here. If he has a question, I'll be happy to answer it.
Yeah, exactly.
Yeah, I saw someone raising a hand, so I don't know
Oh.
if they want to ask a question or.
It's, I think, yeah, I see that too.
We'll stay till every question is answered.
It says it was just to say goodbye.
Oh,
Oh,
okay.
okay.
What she said.
All right.
Very well. All right, then.
Well, may I ask what year you guys went through Mass Challenge? I saw that.
Oh, yeah, that was 2016.
Oh, awesome. My company went through 2017.
Oh.
Cool. Yeah, it was before I joined, so I don't have any particular any experiences this year, but I know the founders was a big boost for Fortify for sure.
Yeah, definitely. I think I'm gonna have to contact you guys soon because we're actually trying to get injection molded components for testing, both ISO and FDA, and we just can't upfront the cost at this time to do a small volume aluminum tool. So
Great.
seems like a good.
Well, you know where to
good
find
option.
it. You do know where to
Yeah.
find it, right? Okay.
Yeah, thanks.
All righty.
Again, Ben, thank you very much.
No
Very
problem.
nice
All right.
presentation.
Cool.
Thank you.
Bye-bye.
Thank you,
I
guys.
can't even end it. It's on you. I'm just going to leave. Bye-bye.
Yeah.